find the kernel. I really like the kernel. I think it is a very intuitive concept. The kernel is more generally associated with a map. Let's say we have a map F, and it takes some input, some values. So the kernel of f of x is all x such that f of x is equal to 0. Does this remind you of something? Yes. When we had a polynomial, this will be the roots of the polynomial. If you have a function, these are the zeros of the function. And it is often interesting to see which values get mapped to 0, because this kind of tells you how much data you've lost. For example, if only one point is sent to 0, then usually this map is bijective. So you have some sort of one-to-one correspondence. If, for example, you have, now you're dealing with matrices, and you have a one-dimensional kernel, then you could say that you have a three-dimensional space, which kind of gets retracted into a two-dimensional one. So you could say that the original matrix shrinks your space. For example, I'm just giving you ideas. Now, what does this have to do with the matrix? Well, remember that matrix is just a linear map. The matrix is just a linear map. And if this is the case, then the kernel of my map A is a map and a matrix. It is all vectors x such that when I multiply my A by x, I get 0. But here this is a different 0. It's a 0 vector. I mean, you probably already know this, but it is a 0 vector. So how do we find the kernel? Well, this is fairly simple, I would say. Just set Ax is equal to 0 and solve. This is really all you need to do. So let's proceed as follows. We would like to say that A times x, a vector of variables, well, this is a three-dimensional map in the sense that it takes a three-dimensional input. You can read this off from the rows, and it outputs a three-dimensional vector, you could say, a vector of length 3. This is also something we understand about the map. The map takes a three-dimensional vector and returns a three-dimensional vector. So this is your input, this is your output. Three-dimensional, and in our case, the output is just simply 0 in each component. This is what the 0 vector is defined to be. And this is a system of equations. It's actually a special case of the general system of equations, which we know how to solve by augmentation. So in this context, we usually proceed with the augmented matrix, which is the case when we take this matrix and we augment the solution, which is 0, 0, and 0, to our matrix. And then we try to make ones and zeros. Immediately, I think you can see that this is an equation that has absolutely no data. If we were to read this equation off, it would say 0x1 plus 0x2 plus 0x3 is equal to 0. And now I want you to take a moment to think about all the x1, x2, and x3 triplets that satisfy this equation. They're all of them, any single triplet of numbers will satisfy this equation, because anything times 0 is 0. So this is not an interesting equation, and we would like to therefore omit it from our set of equations in the following sense. So I write my augmented system, but without the final equation. This is actually a matter of taste. Some people, just leave it as it is, but I think this is important. And if you remember, the publicly stated goal of this process of Gaussian elimination is to have a nice square. We can have the biggest, let's try to have the biggest square we can have. The biggest square we can have here is a two-dimensional square, which is right in front of you. And then let us, we cannot set this to be ones and zeros everywhere else. So let's try to focus on a smaller goal, which is to set this to be our ones and set our goal to make zeros in every other entry that is in this square. So this should be fairly simple. I need to make a 0 here. If I want to make a 0 here, then I will take the second row / equation. I'll multiply it by -2, and then this 2 should cancel out. Now, the best thing about this is that I'm looking at the equation. Did you see this? It's very cool. Anyway, let me try it again. I don't know if I'm looking at the matrix or not, but let me know if I am. That should be very, very cool. This was by mistake. This is not by mistake. Yeah, we are here. We multiplied this row by -2. The best thing is that this times -2 is still 0, so this is unchanged. This times -2 is -2. It cancels out with the 2. And this times -2 is -2. When I add it to 0, it remains as 0. And this is also unchanged because it's just a bunch of zeros. So this is great. And we have our box. We've reached our goal. And now when we reach our goal and we still have some problems with the square format, then we can send this set of values to the other side. Remember that this line is really an equal sign. So I can just do this, that, but don't forget to switch the signs. When we send something to the other side, we need to change the sign. So we do like this. I presume you've seen this before. That's why I'm not thoroughly going into the deepest of details. And now I'm able to read this off as x1 is equal to 2x3 plus 0. x2 is equal to minus x3 plus 0. Well, plus 0. We don't really care about it. Then if I were to write the solution x1, x2, x3, well, x3 is just equal to x3, x2 is equal to minus x3, and x1 is equal to 2x3. Mind you, I will take this x3 as a common factor, and then my solution will become 2 minus 1 and 1. Now, there is a point that I would like to mention, and that is x3 can be any number. We have 3 equations and 2 variables, so we have 1 degree of freedom in the sense. And what this very specific result tells us is that all of the values, all of the vectors on this line, and I hope you agree with me on the fact that this is a line, because you take a vector and you're scaling it with every single possible scaling x3, you take a look at this line. When you apply the map to any point on this line, it gets sent to 0. And that's really the key piece of info that we've obtained from this. So remember, this is a linear map. This linear map always maps this line to 0. This need not be the case with every single matrix / map. You don't need to map whole things to 0. They can just map one point, or just map 0 to 0. But here we have a whole line that just gets mapped to 0, a whole dimension that gets mapped to 0. And this is a very useful piece of info. Now, just for the consistency, in the choices, you'll see something called the span, and you'll see a certain vector. So you're asked to give your answer as the span of some vector. In this case, this would be the vector. Oopsie. This would be the vector. And this is a vector on the line. So when I say the span of this vector, I mean all possible linear combinations of, usually you have more vectors, but here you just have one vector. So if I look at the span of it, the span of a vector is a line. I can always stretch it, and shrink it, this, and that. And you can think of these arrows as scalings of this vector. So indeed, this span is one-dimensional. These two vectors do not line up. This is due to my inaccuracy. Usually they are exactly on the same line. I'm a bad artist, and please ignore that. What I'm saying again is that our line, which let's say this is the vector 2, -1, and 1. Well, it is not. I know it is not because this is in 3-dimensional space, and I'm just drawing something in 2 dimensions. So please bear with me. Let's assume that this is the vector 2, 1, -1, and 1. Then, if I look at its span, I look at all the scalings of this very specific vector. And all of the scalings of this vector means that every single scaling gives you the whole line. And the whole line gets sent to 0. So the span is all possible vectors you can reach just by scaling. Usually it is by scaling and adding, but we only have one vector, so we can add the vector to itself, which is effectively just scaling. Now, just also one more note, because I know this will be confusing for some. The span of 2, -1, and 1 is equal to the span of -2, 1, and -1. What did I do here? I multiplied by -1. Why is this true? Well, let's take a look. First off, I want you to notice that this other vector is just the negative multiple of the blue vector. And I hope you can see now that their span is actually just the same. Because guess what? You're scaling by every single scalar in R. So you take all real numbers. If you multiply all real numbers by a negative number, let's say -1, you still get all real numbers in the sense. The difference is just that you have a different point which you chose. So you could choose any single point on this line, and you look at its span, you would get the whole line back. All you need to have is just a vector on this very broad line. This is a very important point. And because in the end, all the scalings of this vector are exactly all of the scalings of this vector, are exactly all of the scalings of, let's say, this very specific vector, or of that very specific vector. Because if I look at every single scaling, then in the bigger picture, it doesn't really matter. I'm looking at the stretching and shrinking of the vector. It doesn't matter how it will look like, as long as it is on the line, then I can stretch it far off enough, and I can shrink it back enough, and I can flip it to the other side far enough such that I cover all of the line. So I really wanted to clarify this point. You could say this is a mini tutorial on the span of a vector and how to understand this. But I also wanted to additionally address this because it is a common theme. Like usually people find the answer to be 2, -1, and 1, and then they get stuck and they don't know if the answer is 2, -1, and 1, or is it -2, 1, and -1. Well, they're exactly the same thing, because the scalings of this vector give you exactly the same line as the scalings of this vector. And this should be more than enough as a solution. And I can even go further. I can multiply this by 6. So this becomes 12, this becomes 6, this becomes -6. This is still correct. I can multiply by -74.6. And it will still give me a vector on the line. And if it does, then it is more than enough. And I think this is more than enough for this tutorial.